In this video, we're going to show you how to perform a chi-square test on a set of data with two categorical variables. Let's get started. In this example data set, we have two categorical variables. One is called type of position that has two levels, technical or management. There's another categorical variables called performance rating, and it has three levels, three categories: exceeds, fully meets, needs improvement. What we want to do is to see whether there is a relationship between these two variables. That means depending on the type of position that a person's in from the sample, the performance weighting could be different. So that's what the relationship means. So the question is, how do we perform this test? Well, the first thing we need to do is to summarize the data in a contingency table or a cost tab or a two-way table. There are many names for that table, but we need to summarize it in that table, in a table format. In order for us to do that, we can use Excel's pivot table function. So what we need to do is that we need to put our cursor inside the data set that we are looking at. And then we go insert pivot table. And Excel is intelligent enough to expand the coverage of the data to the whole data set that we have, as we can see. Right. So the first step is to specify the range, and this is usually automatic if you put the cursor key inside the data set. So we just have to say OK. And then the next step is to specify what the table looks like. Now the table that we want to see is in this kind of format, right? We have the rows and the column. The rows would be the level of management. The columns would be the performance rating. And so what we have to do is to get Excel to do it for us. So we would click on type of position. By clicking on it, Excel will say, okay, these are the rows that you want to use. And then we have to obviously tell Excel what are the columns. So we're going to take performance rating and we're going to drag it down under the columns bucket. Right, so now we can begin to see the table. All we have to do is to put numbers inside the table. And to do that, all we need to do is just to count the number of respondents in this research into one of those cells. So to do that, what we have to do is to take one of the variables and drag it under summation values, like in this bucket. Excel is intelligent enough to know that the variable that you drag into this box is a categorical variable. So the only statistic you can perform is counting. So you release it, it's just a count of type of position, which is exactly what we have. So out of the 114 observations, is now being classified or cost classified in this table. And this table has many names, as I just said. It's called contingency table, it's called a two-way table, it's also called cost tab or cost tabulation. In any case, this is basically a cost classification between the two categorical variables, and we're going to use it as our starting point for analysis. So let me just copy this content of this table into the format that we want to deal with. So let's just put it over here. So we paste special with values. So, right now we have, so this table, first of all, has two rows and three columns. Right, so the table is also called a 2x3 table because it has two rows and three columns. And each of the combination of the two categories from level management and performance rating is called cell. So we have management exceeds cell, we have management fully meet cell, and so on. So together we have 6 cells. The number is the number of sample point that actually fall into each of the cell. And each one of these number is called the observed frequency. So we have 6 observed frequency. To facilitate the analysis, usually we add one more column and one more row for the table so that we can perform the necessary calculation. The additional column is called the row total. So basically we take the total of each of the row and you put it there, right? So if you look at the formula, this is the sum of all these 3 numbers, and this is obviously the sum of the 3 numbers. On the other hand, we add one more row, which is called the column total. And if you can see that, we just take the total of these 2 columns and put it there, the total of these 2 columns and put it there, and the total of each column and put it there. Then we can either add the column total together, we add these 3 numbers together, or we can add the 2 row total together to come up with a grand total. The grand total is the total of all the cells, and you can see that this is actually the grand total is actually the sample size. So this is how we summarize the data. So the data, of course, is actually just this part. These are the additional row and columns that we added. And the table, as I said one more time, consists of 2 rows and 3 columns. Now, in order for us to do a chi-square test, we need to go through a number of steps. The first step is to calculate what we call an expected frequency. Now, expected frequency is the frequency that we would see in each of the cells if there's no relationship. If there's no relationship, what we see in each cell is basically the frequency that follow the overall pattern, right? So the overall pattern will be the distribution either by the row total or the distribution by the column total. And usually we just use the overall distribution of the row total as a way of simplifying it, right? So the formula for the expected frequency becomes you look at what we expect to see in this cell. Well, we will expect to see out of the total in this column total, they would follow the overall proportion. So you take this number times this number divided by the overall, which is the row I total times the column J total divided by the sample size. And so this is how the expected frequency formula is developed. Now, you don't need to know how they come about if you don't understand what I just said. And all you have to do is to make sure that you know how it's calculated. Okay, so in order for us to do that, we need to use the row total, I, and the column total, J, and divide by the sample size, which is the grand total. So for this one, you need to use the row total for this row, which is 61, and the column total, which is 16. So you take 16 times 61 divided by the sample size, which is 114. So for this cell, it will be 61, right? The row total I times the column total, which is 16, divided by 114, right? Okay, so for this cell, this is the row total, the column total, the grand total. Okay, now let's just do another one, and you can be very clear. So for this one, what is the row total? The row total is still 61. But for this cell, what's the column total? The column total is 62, and the grand total is 114, right? So this one is 61 times 62 divided by 114. Now, you can also use Excel to do it quickly. You can actually do Okay, so E, sorry, F, 4, right? And because I want to copy the formula, I'm going to use the relative absolute addressing times. So this is the row total, so E5, right? So E5. This is the row total times the column total. In this case, is E7, right? E7, E7. Okay, I'm going to have to change it to F5. All right, so F5 times E7, and then divided by the grand total. The grand total is F7. Now the reason why I didn't just I did not just enter F5 times E7 divided by F7 is because of the fact that I want to copy this formula all over. So I just want to do everything all into once. Okay. So let me just check to see whether we're doing it right. Right. So this for this cell, this is the row total. This is the column total divided by the grand total. Now, if you enter the formula right, then what I can do is I can just copy and paste to all of them, right? So I enter it once, I can just do everything, right? So now let's check, right? So because of the fact that I entered properly, so you see that for this cell, the row total is this one, the column total is this one, the grand total is this one. How about this one? Well, this one, for this cell, row total, grand total, row total, column total, grand total, right? So for this one, row total, column total, grand total, right? So it seems like we are entering this way. Now, the reason why we also have the row total and column total again here, there's no use for this number, but we just want to check to see, right? So we can actually just copy the formula here to see whether we are doing it right. If we're doing it right, we should actually have the same column total and the row total, because under the null hypothesis, these are just a redistribution. Okay, so if you check, right, and it looks like okay, and also we should just calculate the row total the same way, right? So it seems like we are doing everything right. So this is how we, the first step in doing the chi-square test is to calculate the expected frequency. The expected frequency is what we expect to see in each of the cells if there's no relationship, right, under the null hypothesis. So under the null hypothesis, this is what we see. So the test statistics is actually quite intuitive, right? We compare what we see, the observed frequency, Fij, with what we expect to see if there's no relationship, right? So this is what we see. This is what we expect to see if there's no relationship. So we would take the difference. So when is it that we would reject the null hypothesis? When the difference between what we see and what we expect to see if there's no relationship is really different. So we take the difference between what we see, observed frequency, and what we expect to see if there's no relationship, right? So we take the difference. But some of them are positive, some of them are negative. So we will see later that those are the numbers that would be what happened. So in order for us to make sure that we can actually do the statistics, we square that number to make sure that all the numbers are positive, and then we divide by the expected frequency so that the problem would have the same scale for every single situation, right? Because some problem is in hundreds, some problems in thousands, and some problem in, so different problem has different sample size, has different scale. So in order for us to remove that scale, we divide that number by the expected frequency. So this is how the statistician come up with the formula, and then we sum them over all cells. And the end result is called a chi-square statistics. Okay, so this is how we calculate the chi-square statistics. So the third step for us is to calculate this part, because we have the observed, which is here, Fij, expected Eij. So we need now, the first step is to calculate this, right? So how do we calculate expected minus observed, or observed minus expected, by the way. I write here expected minus observed, but we can actually do, let me just maybe just change it. Expected minus observed, or observed minus expected is the same, right? Because of the fact that we're going to square that number, right? And then we do square, right? We do square so that they all positive and divide by expected. So let's just calculate everything at the same time. So first of all, we calculate observe my expected C5 minus C12. So C5 minus C12, right? So that's good. That's what we expect to see. And then we square that number, right? And then we divide by the expected, which is C12, right? So that's how we calculate the first step. And then we can, because of the fact that they all line up properly, you can just do it once and copy everything. So now let's just check, right? To check a couple, observe E6 minus expected E13 square divided by E13, right? So it looks okay. So the chi-square statistics then is just the sum of all these numbers. So what we can do, we can just say sum of C19, right, to E20, right? So except we allow you to actually sum all the numbers in this area, and the test statistic is 7.846. Okay, so this is how we calculate the chi-square test statistics. So the question that you will have is that this is actually really cumbersome. Can I actually have a shortcut? Do we have a function in Excel that allow us to do all that automatically? And unfortunately, the answer is unfortunately for the Excel application that come as is from the Office packages, that's the best we can do. Now you can buy an Excel add-in that allow you to do all that work automatically, or you can obviously use a statistical package to do all this work. And usually if you use a commercial statistical package like SAS, like Minitab, like SPSS, they would have the capability of doing the calculation automatically for you, and you don't have to go through this process. So that's the chi-square test statistics. And in order for us to use this, then we need to go through we need to go through the 5-step process. But before we go through the 5-step process, there's another number that we need to calculate. It's what we call the degree of freedoms. The degree of freedom for this chi-square test is actually equal to the number of rows. Let me just write this down for you. The number of rows minus 1 times the number of columns minus 1. Right. So in our case, what do we have? We have how many rows? 2 rows. And how many columns? 3 columns. Right. So this is so important for us to go through that at the very beginning, because otherwise a mistake could be made. Right. So 2 minus 1 times 3 minus 1, which is equal to 1 times 2, which is equal to 2. Okay. So that's how you calculate the degrees of freedom for the chi-square statistics. Now that you have calculated everything, we now can go through the hypothesis test. So how do we specify the 5 steps? The first step is, of course, is the hypothesis. The alternate hypothesis is that there is a relationship between level of position, which is either management or technical, and performance rating. Okay, so that's a very simple way of specifying the alternate hypothesis. The alternate hypothesis says there is a relationship, and therefore the null hypothesis, there's no relationship between the 2 variables. Now that's one style of actually doing the hypothesis. We actually have another style of doing this hypothesis, which is also really popular, right? So another style of doing it would be x0 is that the level of position is independent of performance rating. And HA would be level of position is not independent. Not independent means they're dependent, right? Dependent is dependent of performance rating. Right, so therefore the chi-square test that we're looking at is also called the chi-square test for independence. There are other chi-square tests in statistics, but the one that we're using is called the chi-square test for independence because of the reason why, like that this is the hypothesis that we're trying to test. Now, if you go through the 5-step process, the second step, of course, is we set alpha is equal to 0.05. And then the third step, of course, is if you use the p-value approach, we say reject x0 if p-value is less than alpha. And how do we calculate the p-value? Well, there's actually two ways of doing it. One way of doing it is to use the test statistics and use an Excel function, and then the degree of freedom to do that. That's one way. The other way is actually Excel actually has a function to calculate the p-value after the expected frequency is calculated. So I'm going to show you both, right? So the p-value, since we already calculate the test statistics, is equal to this, right? So I'm going to write it down for you. It's equal to CHISQ bracket. Oh, sorry. Let me just maybe I just do that first, and then we can actually write it up. Right. So CHISQ. Now you can see that when you type in CHISQ, there are various functions that you can use. What we're looking for, of course, is probability. So this is CHISQ DIST. Okay. And so now you are using this function. So Excel tells you what this function is. And 7.846 is the test statistics, right? And then you have the degree of freedom. Degree of freedom, in this case, we just calculate 2 minus 1 times 3 minus 1 is equal to 2. And then just like any other distribution function, we actually have to enter the parameter 2. Now, what happened here is that this function would give you this tail area, right? So chi-square distribution is in general like this. When you get to degree of freedom equal to 3 is like this. Degree of freedom 1 and 2 is like this, right? So those are minor details. But in any case, this function gives you this area. But what we want in the p-value is this area. So what we have to do is to take 1 minus. By the way, because of the fact that the hypothesis test is being specified, the hypothesis being specified this way, chi-square test is always a upper tail test, right? So we calculate test statistic, we look at the upper tail. And what this function will give us is the lower tail. So what we have to do is we have to do 1 minus, okay? And that's, sorry, why do I do that? Okay, and that's the number. So 0.1, let me just make it smaller, right? So the p-value is 0.0198. Okay, so let me just write it out. Let me just put it here and then write it out here, right? So the p-value, if you want to calculate, is 1 minus chi-square dot DIST, right? Not 7.846. 2 and 2. Now, as I said, the other way of doing it is if you are in a hurry, the other way of doing it is as soon as you calculate the expected frequency, we can actually calculate p-value here. I'm going to just put it over here because I want to make sure that I see all the cells, right? So to calculate the p-value, once you calculate the observed frequency, the expected frequency is this. It's called Chi's test, right? So if you type in CXI, you can see that there is a function called chi-sq.tist, so chi-square test, right? And so if you specify that, Excel will tell you that you need to enter the actual range and the expected range. Okay, so the actual range is C5 to E6, right? So that's the actual range. And then you have to enter the expected range. So you still have to calculate the expected value, right? So this is C12 to E13, right? And then Excel now have everything that it needs to calculate the p-value, right? And the p-value, of course, is equal to, if you specify is 0.0198, which is exactly the same as what we calculated. So this is another way of doing it. The good thing about this is that you don't have to go through this step, right? And you don't have to do these steps. You don't have to do this step. And as soon as you finish calculating expected value, if you're using the p-value approach, you get the p-value right away. And so now, so the function that we use is, so let me write down for you, is equal to, right, the chi-square, right, dot test, right, the actual range, right, the actual range, and then the expected range. So that's what you have to do to do the right. So I'm sorry that I actually do that. So you can actually do that and get the same answer, right? So the last step, of course, is that you say since the p-value is equal to 0.0198, which is less than 0.05, we reject x0, and reject x0, we say we have sufficient evidence to conclude, and the conclusion is that the two variables are dependent because they're not independent. Okay, so that's how you perform a chi-square test in detail. Now you say, what happens if I want to use the critical value approach? Well, let's do that, and it's actually pretty straightforward. It would be exactly the same as what we have done before. So if you use the p-value approach, obviously the hypothesis is the same, alpha is the same, right? And the rejection region, of course, is different. As I said, the chi-square test is always, in this situation, is always an upper tail test. So you need to find a value that corresponds to 0.05 here. So how do you find a value that corresponds to 0.05 upper tail? Well, you can use the chi-square table. The chi-square table looks like this, right? So you go to degree of freedom equal to 2, right? Degree of freedom equal to 2, and you go across, and it's 0.05, right? Because the 0.05. So the number that we're looking for is 5.991, right? So you say reject x0 if chi-square test statistic is bigger than 5.991, right? So how do you get 5.991? Well, it's an upper tail test always, and so the tail is in the upper tail. The critical value is the upper tail, and alpha is equal to 0.05, so this area is 0.05. So you can either use the table to find the point that corresponds to the upper area 0.05. Or you say, okay, I don't have a chi-square table, what can I do? Well, if the upper tail is 0.05, how big is the lower tail? The lower tail is 0.95. So we can actually use the chi-square, right, dot inv, right? So we are, again, same thing. And now that you have done a couple of those, you now get a sense, right? If you're given the probability you want to find the point, is inv, right? So inv, right? And you need to put in the probability. The probability is 0.95. Right, so again, if you draw a picture, right, just like every time I do something, I have shown you that it's important for you to draw a picture you can actually see to make sure that you're doing it right. So 0.95, and then the degree of freedom is 2, right? And the answer, of course, is exactly the same as what we get from the table, which is 5.991. And again, we can now use the chi-square test statistics. The chi-square test statistics is sorry, I'm going to do that again, except that I'm going to just paste value so you won't, right? So the p-value is 7.846. So you say since the chi-square is equal to 7.846, which is bigger than 5.991, right? So we reject x0. Okay, so that's how you do it if you do a critical value approach. And because of the fact that we are looking at relationship, the weirdest of them, if ever, that we would actually consider constructing a confidence interval per se in this situation. So that's it for the detail on how to perform a chi-square test, starting from scratch when you have a set of data, and how you can summarize the data in a contingency table, in a two-way table, a crosstab, and then based on that table of observed frequency, you calculate the expected frequency, and then you can calculate the test statistics and the degree of freedom, and you go from there. Obviously, if you have a statistical package, you can actually just go right from the beginning and use that package to generate everything that you need. I hope that you enjoyed this video. I hope that you will see you sometime. Bye for now.